Hi, my name is Afika Dana binti Muhammad Afri. My metric number is 2411127741. Today, I'm going to share my result for Lab 2, where we look closely at how audio signal behave. In this project, we test a 1600 Hz sound tone to see exactly how it changes when you record it from different distance. My main question is how does distance from a sound source affect the waveform amplitude of a recorded audio signal analyzed using Scilab? To answer this, I have two objectives. First, to analyze the waveform amplitude of audio signal recorded at different distance using Scilab. Second, to determine the relationship between distance and signal strength based on peak amplitude. Our independent variable was the distance, which we test at 0, 0.6, 1.2, and 1.8 meter. And we measure the peak wave height as our dependent variable. We predict that as distance goes up, the wave height will go down. This is because sound energy naturally spread out as it travels through the air, leaving less strength for the phone microphone to pick up. Let's look at my test setup shown in this schematic diagram. I use a laptop as my constant sound source and a smartphone to record the file. I use a measure tape to precisely mark my 4 test distance. To make sure my data was reliable, I had very strict control condition. I played the exact same soundtrack at a low volume level every single time, use the same recording device, and keep the phone at the exact same height. My safety precaution rules were also straightforward. I chose a completely quiet indoor space to avoid background noise, make sure the phone was totally stable, and ensure the pad between the laptop and the phone was wide open with no obstacle in the way. Following this step, I saved each track as a dot Wi-Fi and moved them into Scilab. Now let's look at my summary table for data and signal analysis, which tie my whole experiment together. First, there is a clear volume drop every single time we move farther back. My wave starts at a very strong 0.98 volt at 0 meter, but drop all the way down to just 0.11 volts at my farther distance of 1.8 meter. Second, looking at the time domain column, notice the biggest crash happened right at the start. The sound loses over 74% of its initial energy in just the first 16 cm. This behavior perfectly shows the inverse coil law in action because the sound wave quickly spread out to fill the open room, causing energy to weaken super fast. Finally, look at my frequency domain column. Even though the height of my signal peak gets shorter because of this energy loss, its sideways position stays perfectly locked in place. This is a hard finding because it proves that moving across a room makes a sound quiet, but it never changes its actual pitch. Let's see this exact number look when we plot them on our next graph. This slide shows the step-by-step code pipeline my building inside Scilab to automatically process and analyze my audio file. In stage 1, I handled the basic setup by linking my 4 recorded wave audio file directly into the program and set up clear distance label from 0 to 1.8 meter. In stage 2, the code does two important things to make my analysis fair. It converts my stereo phone recording into signal channel mono signal, and it calculates a reference volume baseline from my first recording so all other distance can be compared accurately. Moving to stage 3, this is where the main data transformation happens. The script loops through my file to plot the raw sound signal over time, and then apply a fast Fourier transform to extract the pitch detail into a frequency graph. Finally, in stage 4, I apply custom format to my chart. I add clear label for time, frequency, and amplitude, and I load my graph boundary to show a neat 0.008 second window so the waveform line up beautifully. Let's look at the final overlapping chart generated by this code. Here are the actual overlapping graphs generated directly by my Scilab code. Compare all 4 distances side by side. The top graph displays my original sound signal over a tiny fraction of a second. It can instantly see that the baseline wave at 0 meter has massive wave peak, but a step back to 0.6, 1.2, and 1.8 meter, the wave shrinks down rapidly, provided that the sound loses in energy over distance. The bottom graph shows my Fourier transform frequency spectrum. The key takeaway here is the single sharp spike around 1600 Hz, while the height of this peak drops lower and as lower as distance increase. Its horizontal position stays perfectly locked in exact same place. This confirms that traveling across a room makes a sound quiet, but it never changes its actual pitch. Finally, looking at this line chart, I plot my peak amplitude against distance to see the exact trend. Notice how the line is not straight diagonal, it's dropped in gravity fast right at the beginning between 0 and 0.6 meter, and then start to flatten out as we hit 1.8 meter. This non-linear curve is the ultimate visual proof for my experiment. It perfectly demonstrates how sound gradually naturally decay across open space, giving the definitive physical evidence to prove my hypothesis is correct. Now let's look my debate discussion, which cover three important areas. First, my result perfectly support my hypothesis. Scilab proved that as distance increase, the signal amplitude drops steadily, meaning the outdoor track gets weaker the farther away when moved the phone. Second, for my scientific analysis, this happened because sound waves naturally spread their energy over a larger area as they travel through the room. This matched real physics theory perfectly. The sound volume dropped significantly even though its main pitch stayed the same. Finally, we must look my limitation. Testing in a normal room means I had a slight error from background noise and sound bulge of surrounding wall. However, these results are still highly valuable for real-world engineering, like finding the perfect microphone placement or design better audio recording system. To wrap things up, my laboratory experiment gave my great result that completely support my hypothesis. The data clearly showed that sound wave amplitude dropped steadily over distance because energy naturally spread out to fill a room. Even though my volume dropped by over 18% from started to finish, my FFT analysis proved that the pitch stayed perfectly locked in the entire time. This confirmed that distance weakened a sound loudness, but it never changed its actual tone. Ultimately, using Scilab to automate this work provide the foundation insight needed to solve real-world audio engineering problem. Thank you very much.